Let us start our discussion on number theory with a very important type of number called prime number. Why do I call it an important number? I call it an important number because any natural number n can be expressed as product of primes. Let's say I'm writing here n as product of prime, p1 into a to the power p1 to the power a into p to the power b into p2 to the power c, so on and so forth, where p1, p2, p3 and so on are the prime numbers and a, b, c are whole numbers. A, b, c are any whole number integers. So this prime number forms the basis of all natural writing down all natural numbers. So let me start with something called prime number theorem. So what is prime number theorem? What it states is, if you take up a very large number, any n which is very large, and if you were to find the number of primes up till n, up till n, let's say I'm trying to denote by a function of f of n, and I'm trying to say f of n is a number of primes up to n, then this as established by mathematicians is almost equal to n by natural logarithm of n. So as n goes on increasing and becoming large and large, this value of fn here will almost be same as the number of primes up to n. Let me try to elucidate through an example what I try to mean here. Let me start with a very small value, something like, let's say if I'm taking n is equal to 10. So let me see what is f of 10 here. F of 10 is 10 by ln of 10. Ln of 10 is nothing but 2.3. So this figure here is almost slightly more than 4. So let's say 4.xx. So I'm trying to say that f10, which is 4.xx, is the number of primes up to 10. Let me see, since I've taken a small number, I can actually count them on my fingers. So which are the prime numbers less than 10? 2, 3, 5, 7, and that's it. So we have 4 primes less than 10 or up to 10, and the figure result that I got by finding out the f of 10 is almost, if you take the greatest integer function, the nearest integer to this is almost 4. So this is almost in sync with what we established here, but this is for a very small number, 10. If I took a very large number, let's say it could be 10 to the power 100 or even more, this value of fn will even become more accurater. I mean, as the value of n goes on increasing more and more, the value of fn almost becomes actually equal to the number of primes up to the number. What I'm again trying to say here is that if in other words, what I'm trying to say here is that if I have a very large value of n, the probability that this n is a prime number is nothing but 1 by ln n, 1 by ln n. So what I'm trying to say here is, if I take a very large value of n, which is almost, let's say, approaching infinite or a very big number, I'm trying to say that the probability that or the chance that big number is a prime number is nothing but 1 by ln n. So why can I say that? Because the total the number of primes as expected would be somewhere near this value of fn, which is n by ln n, and I'm trying to divide it by total number of numbers, which is n. So the probability will be 1 by ln n. So this is something, we also say that this is the prime numbers are asymptotically distributed across very large values of n. When you see the representation of prime numbers, if I have very high value of n, if I want to see how many prime numbers are there, they are actually distributed asymptotically, and the number is almost given by n by ln n. So this is a very, very important thing to know. Maybe not that very useful, in your probably in your examinations or something, but it's a very good thing to know, and that gives you the picture of how strong this natural logarithm could be in terms of a tool and the results. So that's the thing here. Now that I have divulged prime number theorem, which is also sometimes called PNT, prime number theorem, let's see, and I went on to say that any natural number n can be represented as a product of primes here. So let's get on to another level here, and I'll try to see how the factors and divisors of n relate to each other. So let me get some space. So let's say I have a number n. Okay, let's start with a very small number. I'll try to deduce a few things here. Let me first write the general expression that I wrote earlier, p to the power b into p to 3 to the power c, so on and so forth. Now let's say I have a natural number, let's say 28. Let's keep a very small number so that I have some ease of calculation, and from there I can try to generalize a few things and then write a general expression of a few things, few parameters and formulas. So what is 28 as expressed as product of primes? It's nothing but 2 square into 7, right? Now let's see what all are the factors of 28. If we can count them on our fingers: 1, 2, 4, 7, 14 and 28. That's it. Okay, so how many number of factors do we have here? There are 6 in number, as we can count from here. There's 6 in number. So basically what all factors do we have? We have 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 0 into 7 to the power 1, 2 to the power 1 into 7 to the power 1, 2 to the power 2 into 7 to the power 1. So what I am trying to do is I am trying to vary 2 to the power 0 through I am taking this chunk, this corresponding to the first prime number. I'm trying to vary its powers, such that they form the factors of 28. So for the first prime number, I can vary those factors from 2 to the power 0 to 2 to the power 2. While for the second prime number, I can do that from 7 to the power 0 to 7 to the power 1. Okay, and since we're multiplying both of these, so the number of factors here are 0 to 2, which is 3 in number, and 0 to 1, which are 2 in number. And the multiplication law of counting says that in case there are numbers like these here, 14, 28, which are composed of multiplication of powers of both these primes. So total number of factors here would be 3 into 2. Just take the product and this will be 6. Understood? Now let me try to generalize here. The number of factors of any natural number n, which is represented like this, would be, now powers of p1 can vary from 0 to a, 0 to a, so 0 to a, so a plus 1 in number, 0 to b for p2, b plus 1 in number, so on and so forth. So ultimately I am trying to say the number of positive factors of n will be a plus 1 into b plus 1 into c plus 1, so on and so forth. The key word here is number of positive factors. Positive. Why positive? Many of people tend to confuse or misunderstand and write this formula for number of factors of n, which is wrong. It should be positive factors, because the number of factors here would be just twice of this. We have only considered the positive factors of 28. If we are also to consider the negative factors of 28, even minus 1 is the negative factor, is a factor of 28, even minus 4 is a factor of 28, even minus 7 is a factor of 28, but we are not taking that into account. So what exactly we're trying to find out is number of positive factors of n, and that will be equal to a plus 1 into b plus 1 into c plus 1. So unless otherwise stated, it must be taken that we are talking about both negative as well as positive factors. Otherwise we must be mentioned there is number of positive factors, and that would be equal to a plus 1 into b plus 1 into c plus 1, and so on and so forth. Okay, now see, this is the basic, very basic thing, knowing the number of positive factors of n and trying to see what's the sum of those, since we discussed that these can vary with the powers of prime number. So obviously if I try to find out the sum of all the factors of n, so I'll have to consider the individual sums of all the factors. So let's say if I were to talk something like this, p1 to the power 0 to p1 to the power let's say a, sum of all these, then p1 to the power p2 to the power b 0 through to p2 to the power b, so on and so forth. So what will be my final sum? It will be actually first of all, if you see, it will be all of these are in geometric progression, because there is common ratio multiplied with each, p1 to the power 0, then p1, then p2. So these are in geometric progression. So it's ultimately the sum of each of the geometric series. So the sum of my all the factors of n, let me represent this by Sn, will be represented by individual geometric series sum of each of these factors. So it will be nothing but p1 to the power a plus 1 minus 1 by p1 minus 1, and law of multiplication of counting, I can directly write it as p2 power a b plus 1 minus 1 p2 minus 1, and so on and so forth. Okay, so these two are the basic things, finding number of positive factors of n and the sum of positive factors of n. Now let's retain this example. Let me clear some space. Yeah, so let me retain this example of 28, which is 2 square into 7. Now I had listed down the positive factors 1, 2, 4, 7, 14 and 28. So just see here, what is this 1 into 28? What is 1 into 28? It's 28. What is 2 into 14? 28. What is 4 into 7? 28. Okay, so if I want to write n or 28 as a product of two numbers, in how many ways can I do that? So if you see here clearly, I have three pairs, and each of the pair multiply to give me 28, or the original number. So in other words, I'm trying to say that there are three such pairs, each of which give me a product of 28. So basically I can write 28 as a product of two numbers in three ways, right? One is, I can do that like this, like this, yeah, and like this. And reverse case, 28 into 1, 14 into 2, 7 into 4 is immaterial, because I have already considered, the order in which I write is not important in this case, because the two numbers that we are interested in is something that we already know. So what I'm trying to say here is, if there was a number n, I'm trying to generalize it from here. So the total number of ways of writing n as a product of two numbers will be what? The number of divisors, positive divisors, which would be a plus 1 into b plus 1 into c plus 1, so on and so forth, as we already found, divided by 2. This will be the total number of ways of writing n as a product of two numbers, only only when, remember, this is possible only when the number n is not a perfect square. N is not a perfect square. Whenever a number n is not a perfect square, the total number of factors are even. Let me take an example. 36 is a perfect square, right? It's written something like this. So what will be the total number of factors? So basically this power will be the power of all the prime numbers must be even if the number n has to be a perfect square. So if all the powers are even, then what will be the number of positive factors? So I have to increase 1 in each of those. So I am increasing 1 to all the even numbers and I am making them all odd, and I'm trying to multiply all the odd numbers. So the number of positive factors of a perfect square is an odd number. So in the case of 28, which was not a perfect square, I have total number of factors as 2 plus 1 into 1 plus 1. So in this case we have an even number of factors, positive factors, which mean that the number that we consider was not a perfect square. And in case of number which is not a perfect square, we simply need to find the number of divisors and divide it by 2 if n is not a perfect square. However, if n is a perfect square, for example in the case of 36, let me try to write down the factors of 36, positive factors of 36. 1, 2, 3, 4, 6, 9, 12, 18, and I have 36. Now how many of them are there? 3, 3, 6, 3, 9, and from here we already found out that it should be 3 into 3, 9. So this is validated. Now in one way I can write 1 into 36, I can also write 2 into 18, I can also write 3 into 12, I can also write 4 into 9, but this is left over. This is something that is left over. But I can always write 6 into 6. I can always write 36 as 6 into 6. So that is not a problem. So all I wanted to know is in how many number ways n or 36 can be written as a product of two numbers. So I can write it as 1 into 36. I can write it as 2 into 18, 3 into 12, 4 into 9, and 6 into 6 as well. So in how many number of ways could I do that? 4 directly, and one extra from the middle number, which is actually the square root of n. So 6 is nothing but a square root of 36. So if you lay down all the factors of n, which with n as a perfect square, there would be a middle number root of n. So that root n will always multiply with root n to give me that middle type of an arrangement wherein that root n will be forming that extra product. So in how many number of ways can we do it here? So total number of factors are 9. Here we had in the case of 28 we had total number of factors as 6, and we did 6 by 2 to get these as the number of ways of writing the products in two numbers. So here what I am going to do is number of factors plus 1 by 2. This is nothing but writing total number of positive factors plus 1 by 2, because there is one number left here which is going to get squared and give me an extra product. So for these numbers I already have a pair. There are 4 pairs, but there is one extra pair which you will get by doing 9 plus 1 by 2, which is equal to 5. So remember, for a perfect square, if n is a perfect square, then the number of ways of writing n as a product of two numbers is number of divisors. Let's say number of divisors are a plus 1 into b plus 1 into c plus 1 into so on and so forth, plus you need to do a 1 plus 1 divided by 2. So this is the number of ways of writing n as a product of two numbers when the number n is a perfect square. Now let me let me end it here, and I'll take up, I'll just take it on from here in the next video.